So yes, thanks for the introduction. So yeah, my name's John Watson. I'm a technical sales specialist at the lead company, and welcome to my presentation, All Hands to the Pumps. So as there we go, as was introduced, it comes from a nautical idiom where you have an emergency and everybody needs to pull together to get yourself out of a tricky situation. So in the terms of all hands to your pumps, the captain used to signal to everybody below, grab a bucket, get a pump, you know, we're sinking, we're going down. Everybody needs to help to get us out of this disaster. So a little bit like this. Found this and I thought it was mildly amusing, so I put that up. But on a serious note, you know, and how all hands to the pumps relates to this presentation today. If we cast our mind back a few years, and I'm amazed to think it's 5 years, we had COVID-19, and that really was a global emergency where everybody had to pull together to do their bit. And you know, this is why it relates to this conference here today, because we had people trying to make ventilators, but one of the biggest elements that we needed to do was improve our ability to test for the disease. So you might remember Tedros Adhanom Ghebreyesus admonished all nations to test. It was the only way that we were going to defeat the virus, was understanding, you know, who contracted it so that we could isolate them and take precautionary steps. And this is what he came up with at the time, that we really needed a rapid and reliable test for understanding who had the disease so we could self-isolate. Now, if we think at the time, and relating this back to the presentation, most test systems actually carry pumps. So I thought all hands to the pumps, and what we did when COVID hit, it made sense. So if you think of the main sort of testing that was used to identify COVID, you've got molecular diagnostics, which has always been the gold standard. So we had lateral flow, but that's a bit like shutting the stable door after the horse is bolted. You know, it's testing for antibodies, and yes, it was a good indicator, but it wasn't really suitable for, you know, picking it up very early stage, testing in schools, hospitals, and the different places it was needed. But with molecular diagnostics, there's a number of sort of drawbacks. You know, it was at the time mostly conducted in labs. You know, we all remember driving to the test collection centres and going through this. I had a small child in school at the time, and every day or so, one of his friends got diagnosed with COVID, and because he'd been in contact, off we went to the local test centre. We'd all queue up in cars and we'd go through. But the biggest issue there was sample turnaround time, or STAT, in the fact that we'd drive up to these test centres, we'd get swabbed, but it'd be 24 to 48 hours before we knew whether we were in the clear, we could send him to school, we could go about our daily life, and away we went. So at the time, there was a real call for more rapid point-of-care testing. And this is where kind of all hands to the pumps comes in, because if you think of most of these diagnostic platforms, there's a pump at the heart of every one of them. So this presentation today is really about how the lead company, we played our bit, we manned the pump, and we used some of our technology to enable and innovate in a lot of the new rapid point-of-care diagnostic systems that came online. So, you know, this is just an example of what we're showing here. You know, I think prior to COVID, PCR would have been a term that not many people knew. After COVID, everybody knew what PCR was. So, if you think of what's needed in one of these diagnostic devices to improve performance, so what they're trying to do is improve your sample turnaround time, or STAT. So quite a lot of them were looking at droplet microfluidics. You know, you can reduce the heating cooling steps. So you need a pump that can enable something like that, for instance. The next is, if you want to make it portable, you don't want a pump that you've got to carry around. You know, space on a doctor's desk is always a premium. So size, weight, and noise also came into it. You don't want a pump that's particularly noisy, that's banging away in the background if you know, you're trying to treat a patient. You've also got the risk of cross-contamination. You need to make sure that every test you do is reliable, and you're not, or don't run the chance of contaminating one test to the other to get false positives or negatives and vice versa. And finally, because the pump is often the heart of the device, you need it to be extremely reliable as well. And finally, this always comes into it, cost. You need to be able to produce a device that is, commercially viable. You can make something that's technically viable and does everything you need, but if it's not commercially viable, then, the chances of it being successful in the marketplace are pretty reduced. So, what did many people turn to for many of their diagnostic systems during this time? Well, they looked at using pressure to move liquids. So, why do we do that? Well, first off, it's clean. If you're using air pressure to move liquids, you've got a natural barrier. You've always got the motive force going to the liquids you're driving. It's also quick. It's not like you have a motor-driven pump with high inertia, which takes a lot of time to ramp up to deliver flow. You can be extremely accurate with pressure. Using air pressure, you can control down to fractions of the millibar, and you can get very, very precise control moving the liquids that way. And then finally, it's simple. So it's very easy to build these kind of systems into your point-of-care diagnostic device, and it's reliable and robust. So if we think about the kind of pumps mechanisms that you use, the syringe pump has been the industry standard for years. Peristaltics are also used, but I don't expect you to take note of all this. I know it's a lot of words. I looked at a presentation guide before standing up and doing this today. It said try not to include too many words, bullet points. So the takeaway from here is, look at the green. Pressure-driven flow ticks way more boxes than syringe and peristaltic pumps. The only real issue there is actually the size. So if you could miniaturize it so that you could put it onto a doctor's desk, you'd be onto a real winner. So this is just an example of a typical pressure-driven flow system. You have a pressure source, you have a pressure regulator, and as you can see, trying to miniaturize that and put that into a point-of-care diagnostic system is a challenge. Well, it was until the lead disc pump came along. So the lead disc pump is a revolutionary pressure source and pressure regulator all in one. I often say it's like an evolutionary step forward in micro pump technology. Over my years, I've been in the world of pumps for about 30 years now. I joke I've sold nearly every type of technology going. And I always say that there's typical pain points with diaphragm, rotary vane, piston, peristaltic, in the fact you've got things like flow pulsation, you've got mechanical vibration, you've got noise, and you've got a lack of control. So why does disc pump differ from that? What makes it unique, and how can I justify my statement that it's an evolutionary step forward? Well, first off, I talked about needing to have compact systems on doctors' desks. Space is always a premium. So you can see here, it's about the size of a €2 coin. Another benefit, silent operation. The disc pump runs at 21 kilohertz, so it's above the range of human hearing. So you can have many pumps running, one pump running, there's no noise. So you can come over to our stand, we're in hall 8A, K09, and you can see multiple pumps running and there's zero noise. So that noise pollution in a care setting is always a big issue. And this is, I think, the most important aspect, is the fact that the pump is pulsation free. So as I mentioned, we're running at 21 kilohertz, so that's 21,000 cycles per second. That's over 400 times faster than an equivalent motor-driven pump. So your flow sensors, your pressure sensor aren't seeing a varying signal. They're seeing a very, very stable signal. So this gives you the accuracy when it comes to moving liquids, in that your pressure sensor or your feedback mechanism knows exactly where it is. And what does this build into? Well, the piezo drive has very little mass and inertia, so we can go from 0 to maximum performance in a matter of milliseconds. So we can follow varying pressure profiles extremely rapidly. So if you need to accelerate liquids, slow liquids, move liquids backwards and forwards, this can be done. And this relates into kind of a near infinite turn down ratio and extremely precise control. So I should really point out at this stage that this pump is only an air pump, a gas pump, and we can only move liquids with pressure-driven flow, but as I said before, pressure-driven flow was the choice of many of these customers that we worked with when COVID hit in developing their point-of-care diagnostic systems. So what did it enable? Well, very accurate flow control. I can see my video's not playing there, so that's... anyway, take it from me, each one of those droplets that should be flowing down there is of equal size. So we talked about droplet digital PCR. So if you can work with very, very small volumes, you can reduce the sample turnaround time because you're reducing things like your heating and cooling steps. Flow response, you need to speed liquids up, slow liquids down, and this is just a brief demonstration of moving liquids through a PCR chip where you can speed it up, slow it down, stop it. So you just have this complete variability with the technology. Next, and I think this is also an important thing, because we're running so fast, there's effectively no flow pulsation, so we can drive liquids in what are called laminar flow streams. This means that liquids mix via diffusion rather than turbulence, and turbulence is a very chaotic and unrepeatable process. So you have a lot of flow variation. Now in a diagnostic test system, what you don't want is variability from test to test. It has to be a very stable system. So with laminar flow, you can move liquids very smoothly, less chance for bubble entrainment. So in any diagnostic chip, bubbles are enemy number one. So smooth flow reduces bubble entrainment and gives you that repeatability. So whilst I've been talking, the video of the gradient chip where we're mixing 3 liquids in a laminar flow stream is actually been running. So if I click the button now, what you should see is we've adjusted the pressure on the red channel, and now we're corrupting the chip. So we're pushing the red liquid through at a much higher rate than the rest, and slowly by surely we're losing the full colour spectrum where those 3 liquids were mixing in that laminar flow stream. So again, extremely repeatable, which is exactly what many of our customers look for in those diagnostic setups and when they're moving liquids through their chips. So I think I've mentioned a few times now about droplet generation and droplet digital PCR. It enables miniaturization. Benefit is you've got faster processing. You're dealing with very, very small volumes, so your heating and cooling steps reduced, the volume of reagents reduced, so your sample turnaround times are faster, your cost per test is lower. Again, reagents can be sometimes the highest cost element in these things. And with this pump you can get very high control. So I can actually see this video is playing where we're actually putting cells inside droplets here, so hopefully that's coming through, you can just about see. Another thing in terms of all hands to the pumps is in many of the laboratories they were doing pipetting systems. So this pump can also be used for pipetting in a very novel way. Historically things like air displacement pipettes were used, but they are limited by the stroke of the pipette. So you can't handle small to large volumes. This pump, by comparison, it doesn't have a stroke. It's not limited by a stroke. So you can do microliters to milliliters and any combination in between. And we were going to have a system running on our stand today, but sadly it doesn't survive transit from the UK to Germany. So you can see a system on our stand. But yeah, sadly it's not operational, but you'll have to trust me, it's very similar to this. So where we have this pump running in a pipetting system for automated liquid handling in laboratories. So as you can see here, it's just moving what we call a staircase, just to demonstrate the very accurate control you can get over moving liquids by aspirating and dispensing. So another area was all hands to the pumps. So I've talked about making the diagnostic devices. You've got to put the cartridges into those devices, so you have to put the reagents onto those. So another big area that we worked in is actually making the diagnostic cartridges. This is where many customers took, again, the lead disc pump because its ability to hold pressure above liquid was critical. If you hold the head pressure above the liquid very accurately, the amount of liquid you dispense onto your diagnostic test cartridge is then governed by the opening time of the valve. So here we took disc pump with a Lee VHS, or very high speed valve, to show how you could spot, down to nanoliter droplets. So we were working with our customers, ramping up their production systems making the test cartridges. So quite often what they would do, they would spot their reagent onto the cartridges, they would then dry the reagent and then seal that so that when it was sent off, the test cartridge had a long shelf life, and then they'd rehydrate during the diagnostic process. So many disc pumps and high-speed valves were used in the production process for developing and making a lot of the diagnostic test cartridges. So, if you read the synopsis for this presentation, it did say, you know, all hands to the pumps and how the lead company did its bit. I felt we did our bit in helping in the fight against COVID. Now, you know, disc pump is just one element of that. You know, in many of these systems, you need to control airflow to get either liquids going backwards and forwards. I showed pipetting, I've showed time metered dosing. So what I would say is disc pump is just one piece of the jigsaw. And for me, when customers come and talk about different applications they're working on, it's understanding the whole system and how you can bring various pieces together, not just as an individual component, but more as a solution. So the lead company is very good because we have many pieces of that jigsaw. And I've just sort of shown up here that, you know, disc pump is an air pump, it sits in the middle, but you've got things like valves, tubings, assemblies, that you can add around that to come up with a solution. So another area that we did quite a lot of work in during the COVID times, and another pump, is our fixed solenoid pumps. So this is a bit like a solenoid valve, but we put a diaphragm on one end, and then every time you shuttle the valve, you dispense a very accurate volume of liquid. So as I said, this pump can only handle liquids with air pressure by creating a positive pressure to move the liquids. This will actually handle liquids directly, but it will do that extremely accurately. And we got various different head materials so you can handle aggressive mediums. So in many systems, you know, disc pump will be doing one element, and this could be on a sort of rinse or a wash cycle, handling aggressive bleaches and cleaning solutions to clean the system after each use. We also have what's called variable displacement pumps as well. So this is a bit like a syringe pump, but it's like a ceramic piston. Again, a very robust mechanism. You can handle liquids directly, or you can handle a buffer solution. So again, you know, we have a demonstration running this on our stand, and you know, we are doing sort of pipetting using one of these pumps. But again, an industry standard. And I think if you cast your mind back to at the start of the presentation, I sort of highlighted the benefits of syringe, peristaltic, and pressure-driven flow. So, you know, pressure-driven flow, you know, will address many things, but it's not the solution to all. So, you know, in many respects, you know, the lead company has a broad breadth of products that we can bring forward to many different applications. So I also talked about miniature control valves. So this is another thing that we brought to bear when COVID hit, because you need to sometimes move the air passage to different channels within a device. So we have a huge array of different control valves, and these are some of the most compact on the market. We have latching valves, we have even quiet valves that pair very well with this pump. Like I said, there's no point having a silent pump if you have a very noisy valve that goes with that. So, you know, we have them in a variety of different materials as well, and these can handle air and what we class as mild liquids. So this is also an interesting one from, like I say, more on the diagnostic test cartridge production. So this is the VHS valve, and it's pretty unique to the lead company in terms of this can be driven up to around 1200 hertz. I think you'll see in our catalogue it says about 1000 hertz, but we can go from a few nanoliters upwards. So if you've got to spot very accurate volumes of liquids onto these test cartridges, this is a great solution. We have various different nozzle varieties and designs, so you can integrate into your various systems. You can also use these for spotting things like air bubbles and liquids into liquids if you put it into a T-junction. So, you know, quite a novel piece of architecture, and it was born out of the print industry, if you think of, you know, drop-on-demand ink printing many years ago. But it's found a home in diagnostics very, very well. We have chemically inert solenoid valves. Again, I say, you know, sometimes you need to move very harsh and aggressive media. So what you don't want is your valve internal swelling because it's not compatible with the media you're handling, and then all of a sudden you have a valve failure. and it causes your instrument to go down. So reliability is always key in many different diagnostic devices. And then finally, I talk of all the pieces of the jigsaw puzzle. We have a whole range of tube sets, nozzles, and various components to link your valves, pumps, whatever you're using. And then finally, I say that the lead company can always do as little or as much as you need us to do. So we have all the different components, but we can bring those components together in a fully tested assembly for you. That can include sensors, a whole array of different things, so that you're not bringing that together and then reliant on testing the integrity. Because leak tightness is absolutely critical. I worked on a system for one diagnostic customer where they're using air pressure to move liquids. And if there was any leaks in the system, then they couldn't understand where the liquid was in the chip at any one time, which is always critical to them. So having a leak-tight system and valves that seal was particularly important. So the lead company, we can bring all those components together and you get out of the box a fully tested, assembled system that is basically plug and play at the end of the day. So I can see I'm slowly running out of time on this, but I'd just like to thank you all for attending today. And because if you've experienced many salesmen, they'll tell you, white is black and black is white. Here's a few testimonials from some of the customers we worked with during that time, during COVID. So, we have basically sort of incorporated Discom into 2 different diagnostic systems here, and it was enabling them to sort of push the boundaries of what they were capable of achieving. So I think I'm almost done. I'll throw it open to the floor for any questions.
Yes, great. And you're not running out of time. You're amazing good timing.
Yeah,
you're fantastic.
Because I did notice it didn't start straight away.
Yeah.
So I was trying to keep track of it. But,
so now the audience have the possibility to ask questions to John.